first up in this session is Yuri.
Okay, I hope you can hear me. So I'm Yuri Levin. I'm a professor at Columbia Physics, and I also have a 20% appointment at CCA, which I enjoy very much. So my COVID activities were trying to figure out the meaning of life and growing ponytail. And both of these quests, I would say, are in progress, very far from being completed. A ponytail gives me particular grief with my family. So I think I'm being bullied by my teenage children quite extensively, but I will persevere. In terms of my research interests, I'm interested in compact objects, neutron stars, black holes, gravitational waves. I spent a lot of time thinking about what makes magnetars move and shine and oscillate and possibly precess, as evidenced by recent periodic fast radio bursts. I also think a lot about superfluids inside neutron stars and how they're connected to glitches. And when I want to get some more observational grounding and somewhat different scales, I think about stellar and gas dynamics in galactic nuclei, in particular, close to the supermassive black hole in our galactic center, Sagittarius A star. My background, my PhD was on LIGO noise, and I still dabble in this occasionally. Most recently, had thought about the thermal deformations of LIGO mirrors, so I'm interested in the engineering side of LIGO. And my most recent passion is cosmic strings. So in fact, in terms of current projects, the project that I'm really working on every day is super radiance on cosmic string loops captured by black holes. So you can talk to me about this. My other project, which I think is quite interesting, is the superfluid flow inside pulsars. I'm finding that this superfluid flows are very inhomogeneous, they form rivers, etc. The paper which I did most recently is on statistical physics of stellar black holes, of Keplerian orbits and galactic nuclei. If you're interested in talking about what stellar black holes do and why, you can talk to me. And also, I've been working for a while on timing features of magnetars, and I'm hoping to finish it also in the next month. So that's it from me.
Awesome. Thanks, Yuri. Do you want to say something about the Stars and Compact Objects group? We got about a minute left.
I think it should be done by Matteo because he and Sasha made this slide together.
Of course. Okay.
Yeah, I can spend a minute or two to...
Great, take a few minutes.
Yeah, thanks. Tell you a little bit about the mission statement and the 5-year plans for the Stars and Compact Object group. So we want to solve very hard problems in computational radiation MHD and relative extreme plasma physics, in particular those problems that we can apply to relevant astrophysical situations. Being at CCA, we want to provide new theoretical and computational ground to exploit the synergies with the other groups and also with the Center for Computational Mathematics. The computational nature of this place means that we want to be ahead of the pack when we talk about developing, maintaining, and contribute open source computational tools and multi-scale algorithms. There are already a number of examples of things we've been doing here, and we want to certainly extend that type of dedication. We think we are already well positioned to become the reference point to the US for computational stellar and plasma physics. For sure, we want to maintain the leadership role for the New York City area and beyond. This leadership role has been a way to bring together a lot of people interested in the things we do and help creating synergies outside of the Flatiron Institute and connecting different institutions. I think we've been very successful at doing that. In terms of building up on this type of knowledge, we want to attract and train the new generation of diverse early career researchers We want to provide a combination of computational theoretical expertise that will uniquely position them to have a fruitful career. Leaving space for serendipity and risky project, I think it's important because it's research, so we never know where we're going. So we want to be always open to new endeavors. And next slide. So what we want to do, what we think we can do for the next 5 years, we want to pave the road towards 3D star evolution, which means stars in 4D. I think that's a future of what we can do and where stars and understanding stars should go. At the same time, we want to develop multi-physics, multi-scale algorithms for extreme plasma astrophysics. And there are a number of possible new directions that we could go forward. Some are listed here. There are more, but we think that coherent radio emission from planets and stars, three-dimensional MHD simulation of convection in stars in terms of making high precision measurement of radial velocities, for example, in the context of a terror hunting experiment. These are all interesting endeavors. And star evolution in exotic environments is something we've been starting doing for AGNs, and coupling dynamics of stellar evolution, and finally machine learning and fluid dynamics. This is all to exploit the synergies that are already existing and creating new one. Similar to what David said, I think that hiring is very important. We work to focus on people and creating a community, and taking risks, moving fast, and exploiting opportunities is our motto.
Great. Thank you. Next up, sorry to cut you short. Okay, good. Next up is Elaine.
Hi, I'm Elaine. I'm joined the CCA group as research analyst in the pre-doc program under the data science team. So my COVID-19 activities, I cut and dye my hair myself, so you can see it's kind of like successful. And also I play Don't Starve Together video game and keep alive in the virtual world as well. And also walk along the river every day for exercise. My research and interest, because I graduate and get the master degree as from NYU as data science. So I'm specialized in machine learning and deep learning applications. So I'm very interested in build various kinds of models, rather like RNN, CNN, and graph nets, and interpret them and find insights afterwards. So my current project is a representation learning of large-scale structure of the universe. Basically, I create the autoencoders, compress information of the universe to a small latent space, and try to interpret and to see whether we have some information about cosmological parameters afterwards. And also another project is start to build like symbolic regression against radioactive turbulence mixing layers using graph nets to find whether we can get like fluid dynamic functions after that. Thank you.
Great, thank you very much. Alexander is up next.
Yeah, hello, my name is Sasha, and I'm pre-doc here, spending my first months at CCA, and in 4 months I'll be done. I came here from the University of New Hampshire, where I'm doing double-sided research of high-energy astrophysics. The one side is numerical simulations of compact binaries like neutron stars, or neutron star black holes. This is what the picture is talking about. And another activity, the research activity, is plasma physics, mostly kinetic plasma physics, but this is theoretical approach, which is I'm trying to incorporate in my models of evolution of the compact binaries. And here I'm kind of stuck in between these two approaches, simulating the plasma physics, not in the astrophysical system, but in the periodic box, and solving high energy, highly magnetized plasma turbulence with resistivity included in the physics, and with test particles on the top of this. And I am doing my research here with Sasha Filipov. And hopefully we will be able to explain how plasma radiates in highly magnetized systems like jets or accretion disks, and so on. And this is probably it for me.
Excellent, thank you. Next up is Lucia.
Hi, I'm Lucia Perez. I hope you can hear me okay. I'm also a pre-doc. I'm a 5th-year PhD student at Arizona State University, but my advisors work on Roman full-time, so I've been at NASA Goddard until this program. My COVID activities included taking my sourdough starter that I'd had since 2018 and actually baking with it. I've been jogging a lot, which is nice because I grew up in Queens, but I don't know in Manhattan below 59th Street. And also Animal Crossing. I'll come back to that if I have time at the end. My research interests generally include the clustering of galaxies and what that can teach you about their morphology or like large scale structure and cosmology, and also Lyman alpha emitters generally and how they interact with ionization. Current projects that I'm wrapping up at home are how we can use different clustering measurements like voids to constrain ionization by leveraging Lyman alpha emitters. Also using the clustering of narrowband emission line galaxies to probe halo occupation. So if you have strong opinions about like halo mass functions, or you've done this, please come talk to me. During these 5 months, I'm working with Shai Janelle to use all my clustering experience with the camel suites, where essentially, if you vary cosmology a little bit in some astrophysical parameters, how does that affect it? What kind of summary statistics might help us train a neural network to tail apart that cosmology? And also maybe what observables might be the best for us to use. And something really cute in Animal Crossing, this owl is named Celeste. She comes to your island when there's a meteor shower and gives you recipes so you can make like giant models of the moon and like space shuttle. So that's something really cute if you are trying to decide if you want to buy this game. Thanks.
Lovely, thank you. There's a coordinating Slack channel going on in the chat here, so stay tuned for Animal Crossing CCA Slack. All right, next up is Alex.
Well, hello, I'm Alex Dittman. I am a grad student at the University of Maryland, also a pre-doc. I feel like this was planned by someone. Yeah, as far as COVID activities, with the collapse of the American academic system, I found it very easy to get distracted by sort of spontaneous passions like making custom color maps or taking some of the N-body work I'd done and adapting that to sort of implicit explicit methods. Generally, I'm interested in numerical methods, compact objects, high energy astrophysics, and I've also alluded to the plasma physics side of this a little with a little plot from a two-stream instability Vlasov-Poisson simulation I ran. So like a little side project that couldn't be featured. As far as the CCA is concerned, I'm largely working with Matteo and Adam on stellar evolution in AGN disks and trying to understand stars, their physics near the Eddington limit. But aside from that, I also work on hydrodynamic simulations of boundary layers and circumbinary disks. And I also work on like orbital dynamics in disks and using X-ray spectral and timing data from the NICER satellite or NICER telescope, I guess, to measure the masses and radii of neutron stars. So, yeah.
Excellent. Thank you very much. Next on the list is Ken.
Hello, everyone. My name is Ken Van Tilburg. I just started as an associate research scientist here at CCA and as assistant professor at NYU. Back when I was still in Santa Barbara during the lockdown, I learned how to surf, which is somewhat harder here logistically. I also like to rock climb. That's also difficult right now, but if anyone's looking for an outdoor climbing partner, let me know. Research-wise, I'm trained as a particle physicist, but I spend most of my time, if not all of it, thinking about different astrophysical and cosmological observables of mostly dark matter, but also about other, also of other new particles and phenomena. And I have several ongoing projects, but just to name 3 of them, over the summer, I wrote a paper pointing out that stars can emit massive particles into bound orbits. sort of tiny fraction of their luminosity forms a sort of halo around the star. And the first two bullet points describe projects looking for decays of these particles in bound orbits around the sun and other stars. And the second bullet point is trying to estimate the evolution of this halo around, in particular, the sun. So on what time scale these particles are ejected from the solar system, and what their phase space looks like after gravitational interaction with the planets. And then finally, I'm thinking, or I'm building out a research program to look for time domain astrometric gravitational lensing of dark matter structures in the Milky Way. So trying to use astrometric surveys like Gaia, maybe future surveys like Roman to look for these structures.
Excellent. Thanks, Ken. Next up is Shirag.
Hey, I'm Chirag Modi. I'm joining Flatiron next month as a CCA and CCM fellow. I just graduated from Berkeley, so the main COVID activity was finishing my thesis, which culminated with a Huggle Rope graduation ceremony that my housemates organized for me at the end of it. Other than that, I like hiking, but once the hiking trails in Bay Area were getting crowded, we decided to go backpacking. So this was my first time backpacking over the pandemic. I also went back to piano, which I used to play when I was a kid. Still not good at it, but if there is interest in the data science band, as was mentioned in the morning, I'll be down to explore piano better. The other thing I explored over pandemic was the computational social science, and I attended a summer school for that of 3 weeks, which gave rise to some projects that I'm pursuing on the side right now, which is like clustering analysis of CalFresh applications and some policy inference and econometrics. I'm still interested in these, and I would like to pursue them further, or other application-based projects at Flatiron with CCA and CCM. But primarily in cosmology, I'm interested in differentiable simulations and forward modeling the universe, with the hope being that we can come up with a unified analysis which combines different cosmological observations consistently for a single analysis. So some of my current projects that I'm doing right now go in this direction. I'm developing a code flow PM, which basically which is a differentiable PM simulation in TensorFlow, and I'm using that for reconstructing cosmological fields that can combine different cosmological data. Yeah.
Lovely. Thank you very much. Next up is Alexandra.
Yeah, that's me. I'm Alexandra. I'm currently a Sagan Fellow at AMNH. I just started last week. So I'm going to be loitering around the CCA for a little bit. And so I guess my COVID activities, like many other people, has been to discover music. And so I'm learning to play guitar, mostly to the detriment of my cats, who can actually tell when I'm doing a bad job and will glare at me. I also like to make homemade tofu, which I will say is amazing. Highly recommend as a fun craft. But my research interests are broadly centered around star and planet formation. So a lot of my thesis, which I just finished up at the U of M, was to do large hydroscale simulations of star cluster formation in order to sort of understand protostellar population properties statistically. But now I'm sort of trying to chug ahead into astrophysical disks, because I really think that protostellar infall is sort of where star and planet formation become very dynamically linked. And so the environment is kind of, the star forming environment is mediated by the disk and should affect planet formation. So I'm really interested to see how essentially disk infall mediated planet formation, when is it efficient? How many structures could you make? Could you collect the ingredients for planet formation for a long enough time in earlier phases? I'm interested in taking more generalized infall models to kind of account for messiness in star formation environments. So things that account for the fact that infall is likely very heterogeneous, both in space and time. And I want to really look into kind of the dynamical implications of this type of infall. So I'm really interested in exploring disk dynamics and the instabilities you can get as a result of infall, like the Rossby wave instability, and of course the gravitational one. So that's mostly me.
Excellent. Thank you very much. Next up is Matt.
Hi there, I'm Matt Orr. I'm a new postdoc starting at Rutgers, and I'll be visiting up at CCA, hopefully at the very least on Fridays, and hopefully 2 days a week, we'll see. But currently I'm out in California, and in my COVID times, I've been doing a lot of hiking and exploring the mountains of the Angeles Crest before the fires, which are mostly under control now. And another fun activity, which is socially distant, doing some astrophotography. So I'm trying to take some pictures of the galaxies that I think about, I guess. And from a science perspective, I'm sort of interested in a combination of using sort of analytic simple models to just, explore star formation scaling relations in disk environments. And I spent my PhD working with the fire simulations and looking at star formation sort of across the disks on everything from 100 parsec scales up to kiloparsec scales, and very interested in sort of pushing on those and using synthetic observations to understand the impacts that our choices in physics, both from the star formation prescription perspective and also the different feedback physics that we include, how those are seen in things like CO or C+. Yeah, so I've sort of broadly been interested in anything that's about Milky Way mass at about Z of 0, but I'm not saying that that's all I'm interested in working on. So I'm very excited to be talking to everyone at the CCA and sort of get to know sort of what everyone's thinking of and sort of the different angles and applications of synthetic observations and feedback, usually in realistic environments, but we'll see. Yeah, thank you.
All right, thanks, Matt. And finally for this session, we have Catherine.
Hi, I am Catherine Johnston. I'm the leader of the Dynamics group at CCA. I'm also faculty in the Astronomy Department at Columbia University. Those are my COVID activities that all have been mentioned by various people. I would just point to one. I have Rachel Somerville to thank for this. Thank you, Rachel, because she inspired me and my family to go to the Adirondacks because we were trying to be socially distanced. We went canoe camping. And without realizing it, the very first night, camped in an island in the middle of the lake with rock going out into the water under the Milky Way on the night of the height of the Perseid meteor shower, which was really spectacular. In general, I'm pretty enthusiastic. I think it's a magnificent time to be a galactic dynamicist. Inspired in particular by the data sets from ESA's Gaia satellite and allowing us to actually observe things we've only read about and thought about in the abstract in the past. For example, had some fun recently with various people, Adrian Price-Whalen, Sarah Pearson, Toma Yavert, exploring signatures of fundamental dynamics on galactic scales. These are sort of signatures that solar system dynamicists and planetary dynamicists get to observe more regularly, things like resonances, chaoses, mapping out separate matrices. The other area I wanted to mention is that when we started the Dynamics group, we did talk about it being bigger than galactic dynamics and not merely galactic dynamics, merely. And I guess I realized actually I have explored another area of dynamics, and that is what I would call people dynamics. And that is something I've been interested in for a while, but the dynamics part comes because of making a connection with an expert on conflict in extreme situations and resolving conflict he works on dynamics of people. So I did actually publish a paper on this back in December, and it's really thinking about what we should be doing today in our field on issues of inclusion and diversity. And as shown in the New York Times last week, why 10%, the top people in power, 10% are women and only 20% are people of color. What does that mean and how is that reflected in our day-to-day life? Next slide. So for the dynamics group, I guess the theme is the Milky Way in disarray. So we've got these beautiful areas, the Bible for us, galactic dynamics, Binney and Tremaine, a rich history, explaining of all dynamics from first principles. It's beautiful. And then we've got magnificent simulations, the galaxy formation group, illustrious, etc. And then we've got observations from the Gaia satellite, and we've got an explosion in data science, machine learning group, the astronomical data group. But we can't help feeling, and many of us have said before, there's something of a disconnect, mismatch between the beautiful idealized study and the other sections here. And so like many of the other groups, we are also trying to make that connection closer. If I jump to topics, the second one, the BFE Collaboratory, is talking about basis function expansions. And this is really trying to create a language to talk across these different sections, a language that's based in basis function expansions, which is solving Poisson's equations. So it's fundamentally dynamics, got dynamics in it all the way through. Other things the group are working on, abundances is dynamical probes. David Hogg has already mentioned this, Adrian Price Whalen, and Melissa Ness, and Emily Cunningham, and myself. We're definitely interested in this. Since the Milky Way is in disarray, it's hard to find conserved quantities in the dynamics around which much of the beautiful theory of galactic dynamics has been built, and my time is up. The last thing is connecting local to global, and I will stop because Will is glaring at me.
Not glaring. You can taper smoothly.
Can I taper smoothly? Okay,
Yes.
The last thing I want to mention is connecting local to global. Sarah Pearson in particular is thinking about this. What can we take learning from the Milky Way to those huge surveys coming up like LSST? And the one person I didn't mention, Jason Hunt, and he's thinking, he's involved in the BFE collaboration, and you should come and talk to all of us. Okay.
Lovely. Thank you very much, Catherine. And thanks everyone for their introductions. We have some questions. The top vote goes to color maps. So Alex, maybe you want to say a few words about what you think about when designing a color map?
Okay, and I apologize, I just started rendering a movie if there's background noise. But my color map design process, one thing I wanted to do was have diverging and sequential color maps that go with various institutions I've had. So I have a nice blue and orange diverging color map for University of Illinois, and I'm trying to capture the black, red, yellow, and white of Maryland decently in a sequential one. But I sort of think in like an HSL color space and then try to transform that to something that's more perceptually uniform.
Can I ask, there is also HUSL, right? Which is another effort. Maybe that's yours, I don't know. To transform HSL to more perceptually uniform.
So I just make something in, I have a fairly generic setup in terms of, I put in sort of the colors I want on one end and the other end, and if I want that to be linear or just split down the middle, one and then the other. And then I transform to the color map with the complicated name that Matplotlib uses to make theirs, CCA or something like that, and sort of fix the lightness distribution there and transform back until it's a valid color map that actually is legitimate.
Cool. Thank you. Okay, actually, I'm curious about the question for Yuri. Yuri, any thoughts on cosmic strings and the latest somewhat anomalous noise in pulsar timing?
No, I have no particular thoughts. I mean, there is some, so that we're on the same page what we're talking about, there is some evidence of common source of noise seen in nanograph pulsars. So it's a hint that maybe they've seen stochastic background of gravitational waves. It's not yet a proof. It's quite far from being a proof, but it's a hint that they've published, and it could really be any kind of source of gravitational waves. But some of the possible contenders are gravitational waves from cosmic string loops, oscillating cosmic string loops, and well, I think it's a good idea. It's probably in terms of your priors, you would probably want to explore first gravitational waves from merging supermassive black holes, but certainly cosmic strings is a potential source. So there's been like 3 papers on this put on the archive just in the past week or so. So people can go and look, but these papers are not as interesting as papers written years ago predicting this sort of stochastic gravitational waves from cosmic strings.
Can I ask a follow-on? What would be the smoking gun for strings versus compact object mergers? It's the frequency spectrum, right?
Yeah, so merging supermassive black holes by virtue of Kepler's laws, they produce, there is a prediction from GR for what should be the slope of these gravitational waves, which is f to the minus 13/3. And cosmic strings generally don't, they have different slope, or in some cases they're not really described by a slope. I would also say that from a theoretical point of view, despite of strings being simple objects, there is no complete consensus between theorists what this background should look like, because you don't really know the spectrum of lengths of small loops that are being produced as a result of that, dynamics of cosmic string network. So there is some theoretical uncertainty.
Excellent. Thank you. Do we have a moment to say things about tofu before we go to the breakout?
Only positive things.
I've managed to reduce a lot of plastic waste by going to the farmer's market, but as a vegetarian, tofu, I have to buy tofu at a grocery store. So I'm very interested in making my own tofu. So I would like to hear more.
I will say that you can buy organic dried soybeans in bulk for like $10 for, I think, 13 pounds. And that will last you for, I don't know how many batches, but a lot of batches of tofu. So it's actually not that hard.
All right.
Do you need to have a blender, or how do you make the soy milk?
So generally you soak the soybeans, you food process them, you heat them up to get rid of the pulp. You get the soy milk, and then you just curdle the soy milk with some sort of emulsive agent. So you can just buy salts and that for this purpose.